Our solar system. We know that our sun is a fairly ordinary middle-aged star that emits vast quantities of radiation that we experience as both light and heat. It is the heart of our solar system, and our solar system includes planets as well as more transient visitors like comets and meteorites. Mercury, Venus, Earth, and Mars are considered the inner planets of our solar system, and they have a very special place in archaeoastronomy. Only the planets Mercury and Venus are closer to the Sun than the Earth. From our perspective, they often appear in the sky as the morning or dusk stars or morning and evening stars, but between these two extremes, they tend to disappear from view as they are engulfed by sunlight. A milestone in a culture's astronomy is when they are able to identify the morning and evening appearances of Mercury and Venus and that they belong to the same entities. As these brightest objects in the sky next to the sun and moon, Venus is venerated around the world. Mars, the next closest object to the Earth, appears to wander across the whole sky. In contrast to the rocky inner planets, the outer planets are gaseous. The outer planets are Jupiter, Saturn, Uranus, and Neptune. Uranus and Neptune were not discovered until modern times, so you do not see them in archaeoastronomy. And the same goes for Pluto, that and other dwarf and exoplanets in our solar system. Another component of archaeoastronomy is the stars. There are a stunning amount of stars viewable from the Earth, but not every speck of light in the sky is a star. Some are planets, some are meteors, and others are true stars. Of the true stars, the brightest, aside from our sun, is Sirius. And it's only about 25 times as luminous as our sun, but it is one of our closest neighbors at only 8.5 light years away. This has made it of particular interest to many cultures, including the ancient Egyptians and many of the North American indigenous peoples. Now, the final big component of beginning archaeoastronomy is the spinning Earth. So, just three key aspects of the Earth's relationship with the Sun underpin most ancient solar alignments. The Earth's 365-day orbit around the Sun is one of them. Another is Earth's daily rotation on its axis. And then finally, the tilt of this axis at 23.4 degrees relative to something called the ecliptic. Now, for those of you unfamiliar, the ecliptic is the plane on which all of the planets orbit the sun and where we believe originally all of the planets formed a disk-like structure of loose spinning material before eventually becoming planets. Now, this tilt is also important. We'll go a little bit more into it because it gives us our seasons. Early cultures had some differing ideas about how the earth moved. And a couple to just note is that the ancient Greeks did imagine that the stars were fixed on a sphere and that sphere rotated around the earth. The other thing that's important to note is that astronomers, even today, have identified or determined that the Earth's North Pole points to a celestial North Pole, and the Earth's equator has a corresponding celestial equator. And just like any position on Earth can be described by its latitude and longitude, so can a position of a star be described in a similar way. However, the terms we use to describe celestial latitude and longitude are right ascension, RA, and declination, DEC, or you'll call them RA and DEC. Because the Earth's tilt, the sun's annual journey across the heavens does not follow the line of the celestial equator. Instead, its path kind of oscillates north and south of the celestial equator, bringing summer to the Earth's northern and southern hemispheres as it does a wobble. These movements culminate in the summer solstice, the longest day of the year, and the winter solstice, the shortest day. Halfway between a solstice and the next, so the summer and the winter, or the winter and the summer, there there's a motion of the sun crossing the celestial equator, and that marks the two equinoxes, and that's when day and night are equal. If we gaze into the midnight sky, each night the stars will appear to move slightly across the sky as the Earth travels a little farther around in its yearly orbit. A star rises 4 minutes earlier each night, but viewed from some locations, some stars never appear to rise or set. They're ever present. These stars are called circumpolar and are seen to revolve around the sky without passing below the horizon. For an observer at either pole, all visible stars are circumpolar. At the equator, no stars are circumpolar. Now, as for the tilt of the Earth, so the tilt of the Earth is Earth's axes, I guess. The tilt of its axes is a legacy from the formative phase of the solar system, probably caused by our planet's collision with another massive object, which kind of knocked it off course. This collision also created the debris that coalesced into our closest neighbor, the moon. And viewed from the Earth, the full moon is a close match to the apparent size of the sun. And this highly unusual coincidence is dramatically evident during every solar eclipse. The moon received plenty of attention from ancient astronomers. Its phases were used as a convenient way of marking time. And some cultures even discovered the so-called lunar standstills, which are the moon's equivalents of solstices, even though the full lunar standstill cycle takes an impressive 18.6 years to complete. So in a nutshell, our solar system is really only a tiny part of our galaxy, the Milky Way, which contains hundreds of billions of stars, and there are hundreds of billions of galaxies in the universe. And so just some food for pondering as we gaze upon the night sky. This thought, I feel like, can bring us closer to the profound sense of wonder and awe with which our ancestors must have viewed the heavens.